Welcome to today's video on integrated rate laws. With integrated rate laws, we are only going to be dealing with reactions that have one reactant. So there's one reactant which we're designating as capital letter A. It might have some coefficient small a, and that decomposes into one or more products. There are only three orders that we will need to consider: zero order, first order, and second order. We are going to be using graphing calculators to determine the order and also the value of the rate constant. All three integrated rate laws are in the form of a line equation, and that form is y equals mx plus b. We know from before that y is the vertical axis, which is the dependent variable. X is the horizontal axis, which is the independent variable. M is the slope of the line, and B is the y-intercept. So we'll talk about zero-order reactions first. For the reaction, A decomposes into products. We have a rate law, and this is what we've calculated before using the method of initial rates. We have rate is equal to a rate constant times the concentration of A raised to the 0 power. We know that anything raised to the 0 power is equal to 1, so really the rate is equal to the rate constant, K. The integrated rate law is in this form. The concentration of A is equal to the negative rate constant times time plus the initial concentration of A. This is in the form of y equals mx plus b. Where did the integrated rate law come from? The integrated rate law comes from calculus, and we do not need to worry about how to derive the integrated rate law. All we need to worry about is using the results of that equation. So these forms of the integrated rate laws will be given to you, and this is the form for zero order. Down below here you see T is time. A sub 0 is the concentration of A at time 0, and A in brackets is the concentration of A at any given time, and of course we know that K is the rate constant. The concentration does not affect the rate of the reaction, so a graph of the concentration versus time should be a straight line with a negative slope. If we can calculate the opposite of the slope of the line, that gives us the value of K, which we know is the rate constant. So let's look at a graph. I see I have a straight line, and on the y-axis is my concentration of A. On my x-axis is the time, and it's sloping downward. So I have a negative slope, and I take the concentration of A divided by time. I can see that the concentration of A is decreasing as time goes on, and when I divide those two, I get negative K. It's negative value because it's a negative slope, and then the value of that slope is equal to the rate constant. Moving on to first order reactions, again dealing with only decomposition reactions with one reactant. We have the form of the rate law, which is rate is equal to the rate constant times the concentration of A raised to the first power. The integrated rate law is using natural log. So I have natural log of the concentration of A is equal to negative rate constant times time plus the natural log of the initial concentration. This is still in the form of y equals mx plus b. When I graph the natural log of the concentration of A versus time, that will give us a straight line if the reaction is first order. If I graph only the concentration versus time or something else versus time and it's not a straight line, then it's not first order. So natural log of the concentration versus time has to give us a straight line. Again, calculating the opposite of the slope gives you the value of the rate constant K. So in my graph example here, I have natural log of the concentration of N2O5. Time is on the x-axis. It's decreasing in a linear way. It's a straight line, which tells us it's first order reaction. For a second order reaction, again, only dealing with decomposition reactions with one reactant. We have the rate law is equal to rate constant K times the concentration of A raised to the second power. The integrated rate law is still in the form of y equals mx plus b, but now I have the inverse of the concentration of A. I have 1 over the concentration of A is equal to K times T plus 1 over the initial concentration of A. It's interesting to note here that K is a positive value, which means K is positive, so I will have a positive slope on my line. When I graph the inverse of the concentration of A versus time, that will give us a straight line if the reaction is second order. Again, the slope of your line gives you the value of your rate constant. So here's my graph. I can see that on the y-axis, I have the inverse of the concentration of C4H6. Time is on the x-axis, and this is giving me a positive slope, a straight line, which tells me it's second order. If I would have graphed the natural log of the concentration of C4H6, I would have gotten a curved line, which would tell me it's not first order, it's another order, and in this case, it's second order. At this point, we're going to do an example with a set of data, so you need to use a graphing calculator. Remember that you can pause the video at any time to input your data and to find the proper buttons. So we're going to look at a set of data. You can pause right now to go find your graphing calculator, and we'll pick up using a set of data. So here's the data that I'm going to use. I have time in one column and the concentration of N2O5 in another column. And the thing that's just different about these types of problems is that now I have time as a data set. When I was calculating initial rates before, we didn't have to deal with time. We were only using concentrations and rates to find the rate law. So now that time is part of our data table, we need to make some graphs to figure out which one is going to give us our straight line. So we'll switch over to our graphing calculator here. I'm going to use a TI-84 model. You might have the same model also. A lot of you might have a TI-83. And if that's the case, the buttons are really similar on the two. If you have a different model, I apologize for that. Hopefully you can still figure out the same buttons, but since most of us have a TI-84 or TI-83, that's what we're going to use for this data. So to use your graphing calculator first, we're going to turn it on, and then I want to enter some data, and so to do that, I'm going to press the stat button right here. So I'll press stat, and the first thing I'm going to do, I need to edit some data. So it's already selected on edit. I'm going to press enter. I see that there's already some data in my calculator, and so I need to clear out that data. If I toggle up to highlight L1, I'm going to clear that data. So I'll press clear and then enter, and that'll clear out any of my other columns. You might have data in some of your other columns. Go ahead and clear out that data now if you need to, but you should have empty looking columns like I have here. We are going to input all of the times, which will go on the x-axis, into L1. So I'll give you a minute to pause the video and enter in the times from the previous slide into your graphing calculator now. Okay, when you have your time data entered in, it should look like I have here in my calculator. Now we're going to toggle over to L2. And what we need to enter into L2 is all of the concentrations from that same data table also. So pause the video here and enter in your concentrations from the previous data slide. Okay, so now you should have your concentrations entered into L2. It's really important to just double check your work at this point because you want to make sure that you have the same number of data pairs. That's a really common mistake that people make. And you also want to make sure that your numbers have been typed in correctly. Again, that's another common mistake that people make. So I have data entered into L1 and L2, and now I want to make a graph. So the way that I'm going to make a graph is I'm going to go to stat plot, and stat plot is right up here. So I need to press the second key and then go to stat plot. So do that. And I want to plot L1 versus L2. And right now I see that that plot is off and there's another plot that's on. So I'm going to select option 1 and I'm going to press enter to make it turn on. And then I need to go up to the other plots and just make sure that those are also off. So plot 2 is off, it looks like. That's what I want. And let's just check plot 3. And that's on. I want to make that one off right now. So I'll just go over to off and press enter. Let's go back up to plot 1 and just make sure all our other settings are right. So the type of graph that I want is the first option, which is a scatter plot. So that's already selected for us. The X list is L1 and the Y list is L2, which is what I have data in right now. And then the mark is just what it's going to show up on the graph. So right now, all of the other settings are looking good. I'm going to press graph at this point. But nothing's showing up on my graph. You didn't do anything wrong. It's just not looking in the right part of the graph. So to fix that, we have to zoom in on the right part of the graph that we want to see the data in. So to do that, we're going right up here to zoom. And we're going to toggle all the way down to number 9. Number 9, which is zoom stat. I press enter, and that will automatically focus your data or your graph onto the right set of data. And I can see from this data that it's curving. It's sloping downward, but it's curving. So remember what we have just graphed at this point. We have graphed concentration of A, in this case N2O5, versus time. We are trying to see right now if this is zero order. Because it's giving me a curved line, all this is telling me is that it's not zero order. It's either first order or second order, so I need to keep trying different options. There's a slick way that I can do those calculations in my graphing calculator, so I don't have to do those on paper. To make some edits to our data table in our graphing calculator, we're going to go back over to stat. We're going to go back into edit, so we'll press enter. And I want to make L3 be the natural log of the concentration of A, or in this case, the concentration of N2O5. And the concentrations, remember, were all in L2. So if I highlight L3 like I have up here, I can type in a function. I can type in an equation to automatically calculate all of that for us. So I'm going to type in natural log, which is over here, and I want to take the natural log of every data set or every data point in L2. So L2 is right up here above the second or above the number 2 key. So I need to press the second button, second L2. Close parentheses and then press enter. And it calculated all of those natural logs for you. Let's just go ahead and do our L4 because we'll want to take the inverse of the concentration of A. We're not going to graph that right away, but we can just get it set up. If I highlight L4 up on the top here, I want to take the inverse of the concentrations from L2. So I'm going to need to press L2 again. So I'll go second L2. And I'm going to want to take the inverse of that, which is my x to the minus 1 key. If I press enter, that automatically calculated all my inverses for me. So at this point, I want to go back and graph L1 and L3 to see if that will give me a straight line. I'm going to go back up to stat plot. So second stat plot. And we want plot 1 to now turn off, and we want plot 2 on. So I can just select plot 1 here and make that turn off. And if I go back up to plot 2 here, let's just double check that I want so my X list is L1 and my Y list is L3, which is what I want. And we'll go up and press graph again. Again, nothing really shows up in my graphing area. That's okay. We just need to zoom into the right spot on our graph. So we'll go up to the zoom button and move down to option 9, zoom stat. And it zooms into the graph for us here. This is looking pretty linear right now, much more so than zero order. So remember what we've graphed at this point. We have graphed time on the x-axis and the natural log of the concentration on the y-axis. If that gives me a straight line, that will tell me it's first order. And right now this is pretty convincing that this reaction is most likely first order. Let's double check though with our second order line to really make sure that this is our best option. So to do that, I'll go back up to stat plot, and I'll make plot 2 turn off and plot 3 turn on. So I'll select off for that one, and plot 3 turn on. And just double check my data. For x is L1 and y is L4, which is the inverse of the concentration. And I'll go ahead and press graph. Nothing shows up, so I'll press zoom. Move down to number 9. Press enter, and here's my data. And this is a curved line. This is sloping upwards. It's a curved line, so it's not second order. The set of data that gave me a straight line was graphing the natural log of the concentration of N2O5 versus time, which tells me that this reaction is first order. Now that I know my reaction is first order, I can find the equation for the line, y equals mx plus b. And if I know what m is, the slope of my line, that will also tell me my rate constant. So I can get the equation from the line using the graphing calculator. I'm going to go back up and press stat, but this time I'm going to go to calc. So instead of edit, I'll move over to calc, and we want option 4, which is to make the equation of the line. So I'll press enter, and right now it's not showing us anything because the default is for L1 and L2. I want to make this calculate for L1 and L3. So I'm going to type in L1 and my comma, and then L3, and then press enter. So this is using A for slope instead of M, but it's the same thing. So A is my slope. A is going to be the rate constant, and on my equation, remember it's a negative slope because it was a negative or a downward facing line. And so if I take the opposite of that, that will give me my rate constant. So my rate constant is positive 0.0069. The B tells me my y-intercept, where the natural log of the concentration intercepts at time 0. So that's really my the natural log of my initial concentration. At this point, you should be able to do an example on your own, so you can go back and review anything you need to in this video about how to use your graphing calculator. There's an example at the end of the study guide that you can try, and there's also book problems that I would like you to do for the next class period. So let's review. We need to remember that all integrated rate laws are in the form of y equals mx plus b. For zero order reaction, I'm graphing the concentration versus time. For first order, I'm graphing natural log of the concentration versus time. And for second order, I'm graphing the inverse of concentration versus time. I use my graphing calculator to find the straight line, and that tells me the order of the reaction. If it's a curved line, all that tells me is that it's not that order of a reaction, it's one of the other two. Okay, hope you enjoyed today's video, and we'll see you back on the next class period.